Yeah. Are you settled after practicals, all of you?
No, sir.
Okay. Right. We are going to start actually, we need to start the third and fourth block in online sessions. That is the reason I'm starting third and fourth block. After completion of third and fourth block, we'll arrange the other online sessions for the first and second block wherever we are pending. Okay. Now I'm going to start the aromaticity. That is, just wait. If you require, I will on my video. Otherwise, I will off it. Okay. Yes. Yeah. My voice is audible to you all. My screen.
Yes, sir.
My
Yes,
screen.
sir. Yes, sir.
Yes. My pen movement.
Yes, sir.
Okay, sir.
Right. Thank you. Now, I'm going to start the block 3. That is titled as aromaticity. Aromaticity. And the properties aromaticity and heterocyclic compounds. Heterocyclic compounds. And then the first unit is concept of aromaticity. In unit 11. Concept of aromaticity. Okay. Already this is the very familiar topic in the degree level. Not only degree, it starts in intermediate level. Okay. That's why I just start with the original concept. First, I'm asking you to one question. Then what are the aromatic compounds? Already we discussed in degree level. Okay, in several organic reactions. Very frequent word we heard. There is aromatic compound. Why we are called it as aromatic?
Sir, which accept 4 and plus 2 pi electron rule.
We just simply say the name. How can you verify the number of electrons in it? How can you say the aromatic by simply pronouncing its name? Is it possible to say whether it is aromatic or not? Okay. Right. Actually, aroma means
Smell.
smell. Yes, correct. The word aroma is the root word for naming this class of compounds. Aroma means a good and pleasant smell. Okay, before the concept of aromaticity, before the identification or discovering of aromatic compound, this word is there. Aroma word is there. Now, when the scientists are working on it, they have discovered some molecules. By simply observing the characteristic order of that compound, they gives the good smell. Those compounds are named as aromatic compounds and aromaticity. Aromaticity means good smelling compounds. Good smelling, right? That is the very trivial word. Okay, but there is no meaning until Muslin and Huckel proposed the concept or theory of aromaticity. Okay, then actually, what are the aromatic compounds? Okay, aromaticity is over based on the smell. We can name it as aromatic. Okay, aroma compounds are aromatic compounds. Right? Then what is the aromatic compound? What is the aromatic compound? When it is said aromatic, when it is called aromatic. These two questions we need to post before starting the listening or understanding about aromatic compounds. Right. Now, according to the definition, aromatic compounds are here the several basis for, defining the aromatic compound. The aromatic compounds are planar, planar. That means all the atoms present in the molecule should be in the two-dimensional plane. That is not a three-dimensional molecule. That is a two-dimensional molecule. Planar. Second one is monocyclic. It is the initial concept, initial definition. Monocyclic. This monocyclic or polycyclic. Or polycyclic. These cyclic compounds with monocyclic or polycyclic with conjugated polyene system. Conjugated polyene system. And containing with four n plus 2,5 electrons is called as aromatic compound. All these things that should be satisfied. Here the where n is equal to, what is the n? The n starts with an integer number 0, 1, 2, 3 and so on. And here in the polyene conjugated system, what is polyene conjugated system? The molecule having multiple number of double bonds, multiple number of 5 bonds. Once the 5 bonds are present in it, all the 5 electrons should be delocalized. Delocalized means all the 5 electrons are equally shared by the whatever the atoms, carbon atoms present in the cycle. Not only carbon atoms, sometimes heteroatom is also there. Heteroatoms like nitrogen, oxygen, sulfur, silicon, beryllium, boron, right? Tellurium, polonium, whatever it may be. Okay. In the ring system or cyclic system, whatever the atoms are linked in the cyclic system, those atoms or elements need to share the 5-electron cloud in equal manner. That compound is known as aromatic compound. Then what are the characteristic features of aromatic compounds? Characteristic features of compound. The main characteristic features of aromatic compounds. What are the characteristic features?
Great thermal stability.
Okay. I hope first class is completed inorganic. Okay. First class inorganic is completed.
Yes, yes.
How many of you attended? All of you attended? Okay, right, okay. I'm asking just to know whether the first class is done or not, I think. Okay. Then, what are the characteristic features? Actually, based on the characteristic features, we are going to identify the aromatic compounds. Right. It has the greater thermodynamic stability. Aromatic compounds are having greater thermodynamic stability because this is the benzene. When it is broken, it generates a cyclic compound, right? A cyclic, a cyclic compound. At the end, there is a like, otherwise you can add one W on one 5. Okay, this is equivalent to a cyclic system, or you can also consider this one also, no problem with that. Okay. These are the comparable acyclic system. This is the cyclic system. Now, when you compare these stabilities, the benzene is having greater thermodynamic stability compared to corresponding acyclic conjugated polyenes and cyclic conjugated polyenes with 4 pi electrons. Cyclic conjugated with 4 pi electrons. For example, this is having 6 pi electrons. The same kind of cyclic system with 4 pi electrons. This is having only 4 pi electrons. This is having same 4 pi electrons. When you're comparing all this, when you give the ranking 1, 2, 3, 4, when you compare the stabilities, right? The first one is more stable than the third one. The third one is more stable than the second one. The second one is more stable than the fourth. Right. Okay. This is the order of stability. Actually, second is also not the stable more than the fourth one. The fourth one is more stable and second. Right. This is the stability order. Why these molecules are comparing? What basis we are comparing the stabilities? When you're coming to these benzene, all the 6 pi electrons, whenever we are representing several times like this, what is the meaning of the circle? What is the meaning of the circle?
Resonance.
Yes, what is the resonance meaning? Delocalization.
Of pi electrons.
Yes, delocalization of pi electron. Delocalization of pi electron cloud. That means the delocalization means all the 6 electrons which will not belong to any one carbon. All the 6 electrons will belong to all carbons. Right? That is called delocalization. Due to the delocalization, once the delocalized electron, those are in the circular manner, equally distributed. There is no deviation, there is no polarity changes. At that time, the molecule system energy becomes decreased. Due to that reason, there is no influence of heat and temperatures. That is the reason those kind of molecules gaining the highest thermodynamic stability. When you are applying the heat, it will not undergoing any structural change. Due to that reason, it is highly thermodynamically stable. Now look at here, these three things are also participating delocalization. Look at here, these are undergoing these 2 pi bonds also produce the delocalized pi electron cloud. This one is also producing the delocalized pi electron cloud, and this one is also generates the pi electron cloud. But this is not continuous in cyclic manner. But in this case, it will be in the circular manner. This is the discontinuous delocalization. This is the continuous delocalization. Right? Can you understand? Right. Then, due to that reason, aromatic compounds are more stable, thermodynamically more stable than when we are compared to their corresponding acyclic conjugated polyenes and corresponding cyclic conjugated polyenes with 4 electrons. This is the cyclic conjugated polyene with 4 electrons, 4 pi electrons, 4 pi electrons. Right. Then whenever we are comparing the 4 and 5 electron system, 4 and 5 or 4 and 2 pi electron system or 4 and 5 electron system. Generally, these are called 4 and 5 or 4 and plus 2 pi electron system is the aromatic system according to the Huckel. According to the Mobius aromaticity, according to the Mobius, 4 and 5 electron system is the aromatic, but according to the Huckel system, it is anti-aromatic. It is anti-aromatic. 4 and 5 electrons containing 5 systems are anti-aromatic systems. 4 and plus 2 pi electrons containing system is the aromatic system, right? These aromatic systems are characterized by some characteristic features. First one is the thermodynamic stability. Aromatic compounds are having higher thermodynamic stability. Aromatic compounds are having greater thermodynamic stability when we compare to corresponding acyclic system, corresponding acyclic systems or acyclic pi system, that is also having pi electron. Acyclic system or corresponding 4 and 5 electron system. This 4 and 5 electron cyclic system, actually. Cyclic system. This one, 4 and 5 cyclic system. This is the 4 and 5 plus 2 cyclic. This is the two are the corresponding acyclic polyene systems. Okay, or 5 systems. Now, this is the first characteristic. For identification of aromatic compound, first you check that whether it is aromatic or not by simply comparing the thermodynamic stabilities. If data is available, or if the facilities are available, we can calculate the thermodynamic stability of each compound, then compare it. Which one is having the greater thermodynamic stability, then we'll decide it whether that compound is the aromatic. Then the all remaining things are maybe aromatic or may not be aromatic, or acyclic compounds are 4 and 5 electron systems. Okay, the second characteristic feature, the chemical reactivity. Chemical reactivity. Aromatic compounds are generally undergoing. Aromatic compounds are unsaturated compounds. When unsaturation, suppose double bond is there, unsaturated compounds. Suppose double bond is there. When this is unsaturated compound. When we are subject to the addition reaction like hydrogenation or bromination, it undergoes to produce a saturated compound with hydrogenation or dibromo product. Addition product will be, that means addition products will be given when unsaturation is present in the molecule. But this is very much unlike behavior by the aromatic compound. Suppose if you are subjected to this bromine, to the bromination reaction that leads to the formation of what the compound generates? Bromobenzene. Okay. Now, it is not the addition reaction, substitution reaction. That means aromatic compounds are showing substitution reactions. That is the characteristic feature. The chemical reactivity characterized by the substitution reaction rather than the addition. Once, suppose if you are understanding here, the addition reaction, after addition reaction, this original structure is changed. That is unsaturated to saturated. Look at here. After performing the substitution reaction, there is no change in the arrangement of pi electrons. Okay, we are showing the two Kekulé structures. These are the two Kekulé structures. Either it is in the any form, both are correct. Okay, but there is no change in the pi electron cloud arrangement after bromination reaction. Therefore, substitution reaction will retain the retention of the aromatic system rather than addition reaction. The addition reaction, if you perform the addition reaction, suppose if it is undergoing addition reaction, we are adding 3 molecules of bromine to the benzene. That maybe we are thinking, yeah, it is produced the 6 hexabromo cyclohexane. If you think hypothetically it is formed. Now what's happening? It is appearing the unsaturated double bond. Okay, but it is not happen when we are subjecting to the bromination. It just generates the bromobenzene. Suppose if you are adding the number of moles of the bromine is increasing, it may be undergoing the substitution reaction 1, 2, 1, 3, 5 tribromobenzene may be generated. Okay, that is depends. That's the conditions we are applied on the reaction. That depends. But addition reaction will not take place. If it is undergoing the addition reaction, the structural changes will happen that will be destroys the aromatic property of compound. But whenever an aromatic compounds are undergoing the substitution reaction, that will not disturb the aromatic character of the molecule. Therefore, aromatic compounds are generally undergoing substitution reaction rather than the addition reaction. However, it is having the unsaturation. Okay, this is the second characteristic feature. Next, third characteristic feature, it is very important to characterize the aromatic compounds. Of course, you are having already completed the practicals in the 4th paper, spectroscopy. In the NMR spectroscopy, especially in the NMR spectroscopy, where you observe the aromatic protons, the range, not the exact value, the range where you are observe the aromatic protons appear in the H1 NMR spectrum. Please let me know. All of you completed your exam, na?
Sir, in the range of 3000 to...
No, I am not asking about the IR spectra. I am asking about the proton NMR spectra or H1 NMR spectra. In the H1 NMR spectra, you will get the peaks.
Yes, sir.
With
Yes.
different non-equivalent protons.
Yes, yes.
For the non-equivalent protons, if the non-equivalent protons are the protons present in the benzene, when you take the NMR spectra of benzene, the proton where it is appeared, where it is gives
Sir,
the
in multiplet, sir.
Suppose if it is benzene, all the protons are similar, equivalent protons. Non-equivalent protons are only one type. Therefore, one peak is observed. That peak is where it is observed in the H1NMR spectrum. I am asking, not the multiplicity I am asking here. I am asking the where it is the chemical shift value.
6.5 to 8 point.
Yes, 6.8 to 8 point. And that is depends on the group present on the aromatic ring. Right. Sometime it maybe gives the multiplates. Okay, sometime it gives the singlet due to the presence of symmetrical substitution. Okay, several things are there, but that is the range 6.8 to 9.9.1. That is the range, or 8.9, the general range. But at the same time, the NMR protons, suppose all the benzene, these protons are appeared at my observation 6.9 delta. This 6.9 delta. Or sometimes if you are increasing, when you are adding any substitution, that will be rises to 7.1, 7.3. That is depends on the substitution present on it. Okay. Suppose I am considering hexatriene system. It is equivalent to, almost equivalent to benzene. Okay. When you conduct the NMR spectra studies for on this molecule, the protons, whatever the protons are there, these are the protons appear on that. Right, these are the protons will be there. These protons are appear in the olefinic region, not in the aromatic region. However, it is having the delocalization. It is also having the delocalization of 5 electrons. But it's showing the range is the protons 5 to 6 delta. This is the olefinic region. Olefinic region. That means the protons present on the aromatic rings are showing the peak above 6.8, 6.9. But the olefinic protons are the corresponding acyclic compound protons are appear in between the 5 and 6. These are the very important characteristic feature shown by the aromatic compound. In the examination, the question may be asked like that. Define the aromatic compound. What are its characteristic features? What are its characteristic features? For that question, you need to define the aromatic compound. In the compound which are planar, monocyclic, and polycyclic with conjugated polyene system containing with 4n plus 2 pi electrons, where n is equal to 0, 1, 2, 3, and so on, which are involving in delocalization of 5 electrons or delocalization framework, that is known as aromatic compound. That is the definition. After defining, you need to explain the characteristic feature. The characteristic features of aromatic compounds are: 1. Aromatic compounds are having the greater thermodynamic stability than their corresponding acyclic conjugate polyene and their corresponding conjugate polyene with 4n pi electrons. This is the first one. Second one, aromatic compounds are giving substitution reaction rather than the addition reactions, unlike to the olefins. Third one, aromatic compounds are shown the peaks above 6.9 in the H1NMR spectra. It is unlike to olefin, which are showing the peaks in between 5 to 6. This is the explanation. This kind of short questions may be appear in the short question answers. Okay. Next, this is about the characteristic features of aromatic compounds. Now, what are the anulines? Next definition is anulin. What is anulin? Anulin may be aromatic or anti-aromatic or non-aromatic. That is depends. And also, I will give you the definitions for these 3 terms also. First, you need to understand what is anulin. What is aniline? The aniline is when you take the, whenever we just think about the aromaticity, immediately we strike, our brain will strike the formula of benzene or the name of benzene. What is the formula? C6H6, right? This is the general case. Based on this, any compound with a CnHn molecular formula Cn and Hn molecular formula is known as any compound with C, not any compound. Here the restriction is there, I'm sorry. Here the restriction is there. What is that restriction? Any planar monocyclic conjugated polyene with CnHn molecular formula is known as aniline. This is the single line definition. What is the aniline? A compound which is a monocyclic and planar. That is, the monocyclic means planar monocyclic conjugated polyene with CnHn molecular formula is known as aniline. The best example is this benzene. The first and best example is. Okay, here anilines may be aromatic or anti-aromatic or non-aromatic. That depends on their property, but that need not to be a aromatic. Okay. Now, how it is shown? C6H6. Aniline always named as is always
amino benzene.
named as N, where N is equal to number of carbons, N aniline. N aniline. Right. Suppose, for example, here the benzene is there. That is called, simply we call it as 6-aniline. In the literature, whenever the aniline is also mentioned with benzene 6-aniline. Benzene 6-aniline. That is also correct. Okay. Or simply you can represent with the only 6-aniline is also correct. 6-aniline is also correct. Now coming to next example, if we take a 4-member ring, that is C4H4. It is known as 4-aniline. In the square brackets, I am representing the number N aniline. And what is its actual name is 1,3 cyclobutene is the original name. But whenever we are understanding the aniline concept, this name is, it is named as 4-aniline, right? Here the aniline sometimes, as per the definition, it should be a planar, but sometimes the aniline may be a planar or non-planar. For example, benzene is planar. Whenever the number of carbons are increasing, 18 anilines are planar. Cyclooctane. Look at here. Cyclooctatetraene. For our convenience, I am writing the planar structure. But it is, what is the shape of this octane? Its conformation is arranged. It is the planar form. It is known as 8-aniline. But it is existing in the tub shape. This is non-planar form. Okay. Even though it is non-planar form, we can express its name as 8-aniline. 8-aniline with non-planar. Okay. Here in the previous case, what you take benzene. If you show the benzene is one kiloform and the other one the second kiloform and a average energy, that is called resonance hybrid. These first two are the resonance structures and third one is the resonance hybrid. We just put the circle. The circle may be put like this, a continuous circle, right? Or you maybe show the circle like this also. Right? But this is the complete aromatic compound. Due to that reason, all the CC bonds and CH bonds have the same length. That is 1.39 angstroms for the CC bond. 1.39 angstroms, almost 1.5 angstroms for the CH bonds. Okay, but when you're coming to this 4-aniline, it will not shown in any way like this. Will not shown by a resonance hybrid structure or in this way like this. Screen is visible to you, right? We cannot show like this because in such case there is a observation that alternate CC bond lengths. This alternate CC bond lengths clearly indicates that, right? Alternate CC bonds. This CC bond is having the 1.46 angstroms. This CC bond is having 1.33 angstroms. And again 1.46 angstroms, 1.33 angstroms. However, it is in the conjugation, double bonds are in the conjugation, in cyclic conjugation. It shows the olefinic behavior, not the conjugated behavior. Whenever they are involving in the what we call perfect delocalization, all the CC bond lengths should be same. All the CC bond lengths should be same. Okay, you can record this class so that you can trace here if it is. Okay, someone is asking like that, you can record this class, sir. Then we can revise it if you do record. Already recording is done. The same lessons will be available in the YouTube. Whatever the recording stories, I will tell you where it is available. I will post the link after the class. Okay. Right. Here we simply observe that alternate double bonds. Here 1.33 angstroms and 1.33 angstroms for the double bonds, 1.46 and 1.46 for the single bond nature. Clearly indicates that the double bonds or single bonds are separated in the that conjugated cyclic system. Therefore, it will not be aromatic. It is not satisfying in any aromatic properties because in the aromatic compounds, once they are involving in the delocalization, all the carbon-carbon bond length should be same. That is 1.39 angstrom. It is the average between the double bond and single bond lengths. Okay, 1.5 plus 1.32. The average is 1.39. That should be arrived in the aromatic compounds. All the CC bond lengths should be 1.39. But in the case of these kind of compounds, this is not a aromatics. Clearly indicate that there is the alternate bond length. These alternate bond lengths clearly indicate that this is not aromatic. Therefore, aniline compounds may be aromatic or may not be aromatic. But that is a aniline. Aniline are having the molecular formula C6, CnHn. Okay. And aniline may be a planar or may not be a planar, non-planar or planar. Okay. There is no relation between the aniline nomenclature or aniline classification with the aromatic compounds. But it is the trivial nomenclature. Whenever we are explaining some of the characteristic properties of aromatic compounds, we are using sometimes this is the so and so aniline, this is the so and so aniline. These anilines may show the aromatic property. These anilines may not be show the maybe anti-aromatic compound. These anilines may be a non-aromatic. We are classified. Okay, this is about the anilines. Anilines which are aromatic, these are having the same bond lengths of CC, same carbon-carbon bond lengths, but whereas anilines which are anti-aromatic, they are behaving like a alternate behavior, that is alternative carbon-carbon bond lengths. Therefore, anilines may be again classified into aromatic anilines and anti-aromatic anilines and non-aromatic anilines also. Okay. Then coming to next, defining what is aromatic, what is non-aromatic, what is anti-aromatic. Simply, first three terms I will give you the only single line definition that you need to elaborate whenever you are writing the examination, right? We have the three terms generally used in the aromaticity lesson. What is aromatic? And second one is the anti-aromatic. Third one is the non-aromatic. I just give the definition. Already this definition is given. What are that? Planar, monocyclic, and polycyclic, conjugated polyene, polyene with what is that? 4n plus 2 5 electrons is known as aromatic. Right? Whenever we are coming to the anti-aromatic, what is the anti-aromatic? Anti-aromatic are also having a similar definition. Actually, this is proposed by the Huckel. But whenever we are considering the Huckel statement, there is the absent. This term is absent. Huckel is clearly mentioned that planar monocyclic conjugated polyene with 4n plus 2 pi electron is known as aromatic. Is not included this word. Okay, later after some theories, some studies, that aromatic compound definition is rearranged like this. Okay, now here anti-aromatic planar monocyclic conjugated monocyclic and polycyclic. polycyclic, conjugated polyene with just 4 and 5 electrons is known as aromatic. Sorry, known as anti-aromatic. This is a simple definition. Next, what is non-aromatic? Here, whether the molecule is having 4 and 5 electrons or 4 and plus 2 5 electrons is a non-planar that comes under non-aromatic. Non-aromatic. Sorry, NO. Non-aromatic. Right? Why, sir, who kept proposing this rule? Why we are avoiding that rule? Yes, we need to avoid. In the definition, he is clearly given the word planar. The molecule should be planar. Otherwise, it is not aromatic. However, it is having 4 and 5. All the condition must be satisfied. The compound should be a planar, a monocyclic, polycyclic. Monocyclic or polycyclic with conjugated polyenes. In this conjugated polyene is also the delocalization is must and should. Delocalization of 5 electrons is must and should. After the delocalization, the carbon-carbon bond length should be equal. Then it is having the 4 and 5, 4 and plus 2 5 electrons. That is known as aromatic. Once any condition is false, that comes under non-aromatic, especially planarity. If planarity is missing, whether it is aromatic or anti-aromatic, that is comes under non-aromatic. That you need to remember. Then the same thing I am explaining in the whatever the just a diagrammatic indication given in your book. It is the energy profile. It is increasing order of energy. Increasing order of energy. Now the aromatic compound, here the comparison is the molecule with the same number of, same size of carbons. When they are comparing, aromatic system is the minimum energy, highly thermodynamic energy, highly stable thermodynamic energy. Thermodynamic stability, sorry. Thermodynamic stability. Aromatic system. Whenever the conjugated acetylene and other some non-aromatics. Conjugated acyclic polyene are large anilines. Large anilines. Once they becomes a large, that is about 26 carbons, and 26 carbons are non-planar automatically. Or we cannot, or these are called as non-aromatic. Non-aromatic. Okay. Now coming to the next one. Compounds which are having 4n electrons are known as anti-aromatic. 4n electrons, 4 and 5 electrons with a planar, monocyclic or polycyclic conjugated bond. It is known as aromatic, anti-aromatic compound. Example, if you take here, it is having the 4n 5 electrons. It is having 4 and 5, or you can indicate like this, 4n plus 2 5 electrons. It's two ways you can express. That is your convenient, 2, 4 and 5. plus 2 electrons. So but most of the books given like this, but in our book is given like above like this. But most of the books represented like 4 and 5 plus 2 electrons. Okay. Or this is also correct. No, there is no deviation, but that is the representation may changes depends on the system, file system. Okay. Now, for the example for aromatic, you very very familiar example. It is benzene, or you can also write that 6-aniline. And 18-aniline. These are the general examples. And coming to the non-aromatic, you have already seen that a tub-shaped cyclooctatetraene. Tub-shaped cyclooctatetraene. Next, for the anti-aromatic, we have several examples are there. What is that? The planar 4-aniline. That is, what is the planar 4-aniline 1,3 cyclobutadiene. Cyclobutadiene. Like this. Right. Or other example. A planar cyclooctane. Cyclooctatetraene. Like this. Right. This should be planar. If it is non-planar, it becomes to non-aromatic. Okay. Then cyclooctatetraene. Right. This is known as simple classification table for aromatic, non-aromatic cation. Once with a molecule with 4 and 5 plus 2 electrons having the maximum delocalization, that is having the higher thermodynamic stability. Now, the regions which are classified, it is called positive resonance energy. Positive resonance energy. This is negative resonance energy. Positive energy, negative energy. How this positive energy or negative resonance energies are occurred? We have the several chemical methods or physical methods are there. Based on that, we can calculate the resonance energy. Then, what is resonance energy? I'm asking you to what is resonance energy? The term is already we heard in degree level. What is resonance energy? Right. What is resonance energy? Any reply for this? Resonance or delocalization energy. For example, you take the benzene and its corresponding cyclooctatetraene. Cyclooctatetraene. Suppose if you want to reduce the benzene to cyclohexane and cyclooctatetraene reduce it to benzene. Sorry, cyclohexane. Then for the both the reactions, the amount of energy it consumes for reduction for each bond or all the bonds. That based on the chemical reactions or based on the physical properties, the difference in the energies or difference in the stabilities or difference in the chemical reactivities that will be quantified. The change in that value of aromatic compound and its corresponding anti-aromatic or non-aromatic system, the difference is called resonance energy. The difference is called yes. Okay, thank you. Okay. Now, how to calculate this resonance limit? The difference is called the exact system. It's a model system. If you calculate any parameter for the aromatic system and calculate the that parameter to the that corresponding model. Suppose if you take the benzene model is cyclohexatriene. Then that is the model. For any parameter you calculate, the value given by the benzene and the value given by the cyclohexatriene, just you observe the difference. That is the suppose the value came from the cyclohexatriene is X and the value came from the benzene is Y, X minus Y. If it is the positive value, that is called positive resonance energy. If it is the negative, that is called negative resonance. Similarly, that means the parameters may be hydrogenation of cyclohexane, hydrogenation of benzene, and hydrogenation of cyclobenzenes. Okay, or heat of combustion, right? Based on these values, we can calculate the resonance energy. That resonance energy may be a positive or may be a negative. If the resonance is positive energy, that is called aromatic in nature. The resonance energy is negative, that is called anti-aromatic. If that is equal to the or resonance equal means the difference is zero, that is called non-aromatic. Nearly zero or zero value, that is called non-aromatic compound. Okay, in this way we can classify the compounds anti-aromatic, non-aromatic, and aromatic. Okay. Uh, uh, for the benzene, we can calculate the resonance energy. The resonance energy of benzene. Just I am taking the of benzene. It will be calculated by the heat of hydration method. Heat of hydrogenation. Hydrogenation method. Heat of hydrogenation method. What is heat of hydrogenation? You just any double bond is there if you are adding hydrogen. It takes some energy. Okay, then it leads to the formation of this saturated compound. Okay, here also you take the cyclohexene, only one double bond is there, cyclohexene. Whenever it is subject to heat of hydrogenation, it requires 120 kilocalories, kilojoules per mole, kilojoules per mole. Then it leads to produces cyclohexene. Similarly, you take the cyclohexadiene. For one double bond, it is 120. It takes the addition of 4 hydrogens to the hexadiene. It consumes 208. 208. Benzene, first benzene తీసుకోండి, general benzene తీసుకోండి. It is in the resonance structure. Right. It takes 208 kilojoules per mole to produce the same product. Look at here, for one bond, it takes the 120 kilojoules. Now, it's the benzene model structure is cyclohexatriene. Cyclohexatriene. Therefore, it is having 3 double bonds are there. The 3 double bonds into 120. That means 360 kilojoules per mole for the reduction of the or hydrogenation of the benzene model. For actual benzene, how much it takes? Just it takes 208 kilojoules per mole. Now, what is the difference? This is the difference. 360 minus 208. What is the difference? Almost 152 kilojoules of per mole energy is difference. Now, this is called resonance energy. Now, after you are observing that, it is the positive value, positive resonance value. Therefore, it is aromatic. Based on that, we can calculate the resonance energy by using simple method, heat of hydrogenation, heat of combustion, like that. Okay. But for every organ, if every aromatic compound, it is not possible to calculate the resonance energy because there may be not available the model compound. If in the case of benzene, it is available, that is the cyclohexene or cyclohexadiene or cyclohexatriene is available. Cyclohexatriene is not available. We known that cyclohexene and cyclohexadiene. After conducting the heat of hydrogenation on that molecule, for the first molecule cyclohexane, it consumes the 120 kilojoules mole of energy, kilojoules of energy per mole, and for hexadiene, it takes a 240 kilojoules of energy. Based on that, we are calculating the if the cyclohexatriene is having 3 double bonds. Therefore, from that we are calculating 360. That is the calculated value. And directly we conduct the experiment on the benzene on the heat of hydrogenation in the presence of catalyst. Therefore, it produces cyclohexane. It consumes the 208 kilojoules per mole. After the difference, we results that 150 kilojoules. That is the positive value. But every aromatic molecule, this is not possible because the model is not available for all the cases. Hence, we cannot calculate the resonance energy for this by using these chemical methods. Okay, but we can calculate the resonance energy by using molecular orbital theory and some other explanations. We can calculate it. Okay. Today I am going to stop the lesson. Tomorrow I will continue some criteria for aromaticity and Proust-Muslin diagram and explanation of molecular orbital theory and so on. Okay. Thank you for your cooperation. If you have any doubts, you can ask me. I will take up the questions.
Thank you, sir. Good day, sir.
Good day. Who is talking? Is there any people from Vizag or Warangal, Tirupati?
Varangal, sir. Myself is Varangal.
Okay,
And
good.
my name is Venkatram.
Venkatram. Okay.
Sir, one small doubt, sir.
Yes.
Yeah, here we are calculating the heat of hydrogens now. So bond energy of formation, plus bond energy of dissociation of bonds. No, the formula for this Kekulé formula we are using. No?
You're using the Kekulé formula. For Kekulé formula, Kekulé model, Kekulé model of benzene, we have the model is there. That is the cyclohexene is there for single bond, cyclohexadiene is there. But once you are talking about the cyclohexatriene, we are inserting the third double bond in it. Delocalization is happen. That is equal to benzene. That's why we are not taking the cyclohexatriene. That is the only hypothetical only, the model piece only. Real whenever we are when we coming to the reality, the benzene is the cyclohexatriene. Okay. For calculating the amount of energy consumed for the 3 double bond reduction is based on the amount of energy taken by the one single bond present in the cyclohexene and 2 double bonds are present in the cyclohexadiene. Based on that, we are calculating the third one.
Third one, yes, sir.
Based on that, we are calculated. Okay.
Yes, sir.
All these things are we are studied in the degree level. Okay.
Yes, sir. Yes, sir.
Just I have revise it. Just recollect it. Okay. From tomorrow onwards, we will go to the actual topics. Okay. Criteria of aromaticity and post-Muslim diagrams. Huckel molecular adapter theory. What is the rationalization of Huckel theory, and what is the benzenoids and non-benzenoids? Okay, those concepts we are going to discuss from tomorrow. Okay.
Thank you, sir.
Thank you very much.